day, ladies and gentlemen, and welcome to the Quasi Cyberseminar conference call. My name is Rachel, and I will be your coordinator for today. At this time, all participants are in a listen-only mode. We will be facilitating a question-and-answer session towards the end of this conference. If at any time you require assistance, please press star followed by 0, and a coordinator will be happy to assist you. I would now like to turn the presentation over to your host for today's call, Mr. John Duncan, Communications Director. Please proceed, sir.
Thanks, Rachel. Well, welcome, everybody. Glad to have you on board today for the talk by David Tuck, Time for a New Dimension in Capillary Pressure Saturation Space. So again, for those of you who are becoming regulars now, this is the second semester of these Education and Outreach Distinguished Lectures. If you have any problems, please send a chat to me or hit *0, as Rachel told you. And we're always looking for feedback, so if you could send an email to me at commanager, COMMGR, @quasi.org, it's greatly appreciated. So your phones are muted. If you have any questions that you'd like clarification on, any points you'd like clarification on during the talk, please let me know and I'll jump in and ask Dave. But otherwise, wait to the end of the talk and we'll open it up for questions and answers. And you can get to the operator by hitting *1 and ask your question directly or type it into the chat box. So to practice that chat window, we're still looking for how many people are participating at your institution today, just so we can get a ballpark estimate of how many folks we're reaching with this service. And we're still in the testing phase here, so if you have any questions on the technology or problems, please let us know. We do have one more this semester. That's going to be April 9th by Matt Moore of the National Sedimentation Lab. The title of his talk is What Role Do Ecologic and Hydrologic Research Play in the PMDL Process? So we're very proud and happy to have David M. Tuck here. Dr. Tuck has got 2 bachelor's degrees in chemistry and geology. He spent 5 years after his bachelor's working for an environmental consulting firm in Grand Rapids, Michigan. He then went back to school for a PhD from Princeton University and graduated from there in 1992. He spent 7 years working for the Westinghouse-Savannah River Company in Aiken, South Carolina, where the seeds of the research he's presenting today were planted and began to grow. He left Westinghouse in 1999 and started Napologic, a research and consulting company where he's the boss of himself, I guess it is. And I've recently found out that he also spent a fun but disastrous year teaching high school physics. So maybe we can ask some questions about that at the end. Dave, I'm going to turn the presentation over to you, and you should be set.
Okay, thanks, John. First, I'd like to start with a beg for your forgiveness. I have a tendency to have fun playing with words. There's actually a double entendre in my title. First is that it is time for a new dimension when we talk about and try to understand capillary pressure and saturation relationships in porous media when we're modeling multiphase fluid flow. The other is that time is, in fact, that new dimension. I want to start with acknowledging the people that have helped me with developing these ideas and the research that I'll be presenting today. There's actually 2 parts to the talk. If we have time after the conclusions of the main part of the talk, I'll go into that second part, and if there's also interest. The people that helped me primarily in the first part of the talk include Bill Perkle and Gary Iverson at the University of South Carolina, Aiken Bay, who did most of the interfacial chemistry measurements. In the second part of the talk, I worked with Peter Jaffe and Mike Celia, professors at Princeton University, Shobai Sun, who was a postdoc, and 2 graduate students, John Johnson and Paul Reeves. Also, Paul Nimhoff at the University of Delaware helped a great deal with that, some of that work, and Greg Flack at the Westinghouse-Savannah River Company. I'm going to go a brief overview of the talk. I'm going to indulge another pleasure of mine, and that is the history of science and the history behind some of the ideas that we'll be talking about that are important in understanding multiphase fluid flow in porous media. Then we'll go in and talk about what that importance is, how the interfacial chemistry plays a role in understanding multiphase flow in porous media. Then we'll get into the real details of how the interfacial chemical kinetics that try and convince you that this is real, I'll give you some results from a small modeling study that I did, and then also some experimental results that confirm that I think this is an important issue. At that point, we'll just talk about the conclusions from this first part of the talk. Then if we have time, I'll go into the time dependence during imbibition. That is, this is the more important aspect when it comes to thinking about how we remediate an aquifer when it's been contaminated by DNAPL, or in the case of the oil industry, when they're interested in, say, secondary or tertiary recovery of oil from a trap. Those are primarily kind of preliminary thoughts and some experimental results. Okay, so here we go with a brief history of time in interfacial chemistry, with my apologies to Stephen Hawking. There are two main primary references that develop the fundamentals of capillary forces which we're interested in, which we need to understand for multiphase fluid flow and porous media. The first of those was Young's equation in 1805, and then also Laplace's equation in 1806. When we combine those two, we get the Young-Laplace equation, which is the fundamental equation we need to understand capillary pressure and saturation in a porous medium. First, let's talk about the Young equation. This was published, as I said, in 1805. What he did was look between interfacial forces, and he balanced the interfacial tension between the two fluids, in this case the, let me get my pointer here, MOW, with the interfacial tensions between the water phase and the solid phase, and the interfacial tension between a solid and an oil. And the balance comes through the contact angle. So Young explicitly recognized the importance of contact angle along with the interfacial tension forces that act during this mechanical balance. One caveat is that, historically interesting, is that Young's paper is entirely in text. There are no equations presented in it per se. The equations are all described verbally. So it's an interesting study in how the use of mathematics and mathematical symbolism helps enhance our understanding of a paper. Then let's go to talk about Laplace. He published his work in 1806, and he recognized the two primary radii of curvature of an interface between between two fluids, which I've indicated here in this graphic. He made the assumption that the contact angle was 0 as the interface merged with a wetting film on a solid surface. But he did a lot of work with looking at non-cylindrically symmetrical systems and how the interface, or the shape that the interface would take in those forms, with the limitation that he didn't include contact angle explicitly. So now what we come to, we look at the incorporation of, or the melding of the two equations, the Young-Laplace equation, where we have a pressure difference between an oil phase and a water phase, which is defined as the capillary pressure. And that's balanced, or that's defined by the interfacial tension between the oil and water, a contact angle that the interface makes at the solid interface, and the two radii of curvature. We talk about this whole entity as being the mean curvature of the interface. Going on from there, these are variations of the Young-Laplace equation, which are important in understanding multiphase flow and porous media. One of the earliest ones was the Washburn equation from 1921, in which he used the rearrangement of the Young-Laplace equation to define a pore radii through which an immiscible fluid was passing during its infiltration of a porous media. This equation is the fundamental equation that's used to develop pore throat size distributions in porous media. The next variation on the Young-Laplace equation was the Hobson's equation. Hobson used this equation to look at gravitationally stable thickness of oil in a trap. I'm illustrating that here. In this situation, Hobson assumes that the oil was less dense than the water, and that the gravitationally stable height of a ganglion of oil in a oil trap is controlled by the capillary force at the bottom of the ganglia and the capillary force at the top of the ganglia. And this is the equation that he developed. So you can get the H would then represent the gravitationally stable thickness of oil within a trap, which is of obvious interest to those in the oil industry in terms of estimating how much oil is present in a reservoir. For my own interests, I've been more interested in DNAPLs, in which case this would just be flipped, and the trapping interface would be the lower interface rather than the upper interface. In this situation with DNAPLs, where the oil is more dense than water, the gravitational force is downward, versus the situation Hobson was concerned with, in which the gravitational force is upward. Okay. All right. Now it's time to point out that all of those equations that we've discussed above assume equilibrium interfacial chemistry. That's an important point to make. In some of my presentations of the work that I'm talking about today, someone has commented that interfacial chemistry is equilibrium, and that's not necessarily the case, and that's what I'm going to talk about now. Time dependence in interfacial chemistry, or interfacial tension, has been known for more than a century. Dupre in 1869 examined the interface or surface tension of aqueous soap solutions and noticed that the surface tension decreased. In 1890, Lord Rayleigh developed a jet method for surface tension, which allowed the time scale of variation of surface tension to be measured on the order of seconds and less. In 1907, Milner also did experiments with sodium oleate solutions and observed that surface tension varies with time. That there was an initial rapid decrease in the interfacial tension, and then a slow approach to a steady value. And he suggested that diffusion of surface active components in the water phase fusing to the air-water interface was what controlled the time dependence of the surface tension. In 1932, Bigelow did further work along those lines, and he has a wonderful bibliography that helps point out historical references. Paper that's of interest to me in 1936, Gibby and Addison showed that there's surface activity of dyes at Napa water interfaces. And much of my work has come about through my working with a particular dye, which we'll talk about, Sudan 4, in a tetrachloroethylene water glass system. So the idea that dyes are surface active is, again, not new. Of course, it's always disappointing as a person, as a researcher. You always want to think that your discoveries are the first, but often that's not the case. Bond and Poles in 1937 looked at interfacial tension timescales. For pure liquids, they determined that equilibrium interfacial tension was established within 0.005 of a second. That was the limitation of their. They suggested that time scale is actually probably on the order of 10 to the minus 9 seconds. interfacial tension is established very rapidly. When we go to solutions, that's not necessarily the case. It depends on the solute and the components of the system that you're working with. Ward and Prodai in 1946 explicitly fitted time dependence to the diffusion equation. Here's just a listing of the time scales for surface interfacial tension, and therefore capillary forces in a porous medium. Thomas and Potter and Zhang and Zhao measured time scales of equilibrium being established on the order of milliseconds. Laplace and Giles and some of my own work with Tuck and Rules in 1999 demonstrated equilibrium or processes occurring in the time scale of seconds to minutes. Pan, 1998, interfacial chemical time scales on the order of minutes to hours, and also it goes to hours and days and longer. Okay, from that, we conclude that it's not necessarily appropriate to assume interfacial chemical equilibrium during dynamic processes. And when we're talking about the motion of multiple fluids through a porous media, we're talking about a dynamic process. Okay, so how does that time dependence of interfacial chemistry arise and therefore influence multiphase fluid flow in porous media? Excuse me a second. This is a legend. I'm going to show you a series of 6 schematics where I schematically illustrate how chemical kinetics arises during primary drainage of a DNAPL as it penetrates a water-wet porous medium. These are the mineral grains. I assume a nice spherical grain for simplicity. The red is NAPL. Light blue is the aqueous phase. Here we have surfactant molecules that are dissolved in the bulk NAPL phase. In the experimental work that I'll present in a little bit, this is the case. In this situation, in my particular situation, these surfactant molecules are actually dye molecules that we use to dye an apple with. I get that red color, hence the red for the NAPL. And this illustrates surfactant molecules that have adsorbed at the NAPL-aqueous interface. It is this adsorption of surface active molecules which decreases the surface tension, or interfacial tension in the case of liquids and liquids, or the surface between a liquid and a liquid, and therefore reduce the capillary forces. Reduction of capillary forces makes an oil or a DNAPL more mobile in a porous medium. And this is schematic surface surfactant, or excuse me, schematic surfactant surface excess. Try to say that fast 4 times. It is the surface excess of surfactant which causes the reduction in interfacial tension. And that was demonstrated by Willard Gibbs, again, over a century ago. All right. So here we're going to talk about a schematic presentation. Here's my porous medium with 4 spherical grains. We have just established an interface. This is a fresh interface. I'm going to say this is time 0. And the initial concentration, initial surface excess of the surfactant molecules at that interface, and again, this is highly schematic, please understand that, is 2. And this surface excess and the resulting interfacial tension establishes or determines where that interface is stable within this specific pore throat. As time goes on, then let's talk about a schematic time equal to 1. Some of these surface active molecules have adsorbed and partitioned into the interface. This reduced the interfacial tension and therefore allows the interface to move down or creep into the pore throat. Now, what I've done here, here's my schematic. schematic surface excess, there's 4 molecules in the surface. There's also 2 components of this interfacial excess. One is just the number of molecules that absorb into the interface, but there's also a compression of the interface as it migrates down into the pore throat towards, or migrates further into the pore throat before it finally reaches the critical radius here at the very smallest constriction of the pore. And now with time 3, we have a surface excess of 6, and I use the pluses, plus, and then there's further compression of that interface. It's critical limit of stability in this given pore throat. As time goes on further, a little bit more adsorption takes place, a little bit more compression takes place, and that pore throat, or that interface, is no longer stable in this pore. What happens, this is the beginning of a Haynes jump. And a Haynes jump is the movement of an interface from a pore throat into the next pore, or through the next pore, or a series of pores it can actually be. And this occurs extremely rapidly. There's been some work that I've seen that suggests that the pore Haynes jumps can occur on time scales of less than thousandths of a second. Can jump several. So this process is extremely fast. Again, the interface progresses further through the pore body, and the surface excess is diminished further as that as that interface dilates during its movement through the pore body. Finally, we come to the establishment of 3 new interfaces. But these all have interfacial age of 0, and again, by the assumptions that I've made in this schematic, all of the interfaces are equivalent. This is isotropic and homogeneous porous medium. And we have 3 new interfaces established with, again, surface excesses of 2. Again, please remember that these are highly schematic. It's a highly schematic illustration. But the point is that because of the rapid nature of the Haynes jumps, it isn't necessarily appropriate to assume equilibrium chemistry when we look at the pore throat or capillary forces. All right, I'm now going to move on to talking about the specific experimental system which I've worked with over the last 6 to 8 years. The liquids are water and tetrachloroethylene, or PCE, and the dye, Sudan 4, which is illustrated here. The dye is surface active because of this hydroxyl group, and probably also because of these nitrogen-nitrogen double bonds. Ring structures have also been shown to have play a role in surface activity. Phase that we looked at was glass, in particular glass beads. Right here is an illustration of the time dependence of, in this case, surface interfacial tension, I should say, between water and the dyed PCEs as a function of interface age in seconds, and here on the legend, the concentration of dye in the NAPL phase. You see here is a concentration of 0. Now you note here that there is a minor decline or decrease in the interfacial tension. That's actually due to the fact that the PCE we used had something like 1% ethyl alcohol or ethanol in it as a preservative. And so that time dependence right there is probably due to the surface active nature of the ethanol within that system. As we increase the dye concentrations going down here, you see the magnitude of the interfacial tension reduction increases, and also the time dependence of that interfacial tension reduction decreases. One thing I'd like to point out is this curve and this curve. These concentrations, actually I should say, where am I? Yeah, this one and this one. These two concentrations are on the order of dye concentrations that have typically been used in studies of multi-phase flow in porous media. As you can see, there's significant decreases in interfacial tension with the age of the interface. That means that the capillary motion of an interface during primary drainage is decreasing as the age of that interface increases.
Dave, can I just jump in for a second? I've got a point of clarification.
Yep.
Someone would like to know how these IFT measurements are made and what the geometry is.
Actually, that's a very good question. It's a drop volume technique where you use a syringe pump to control the rate of the drop formation and therefore the average interface age. As you pump the fluid or make the drops occur more rapidly, that's this end of the scale, the interfacial tension is higher. As you slow down the pumping rate or the rate of formation of the drops from which the interfacial tension is measured, the average interface age increases, and that's over at this end of things. Regarding how accurate this is, I'll point out that this curve here with the 0.04, I'm sorry, this one right here, the 0.411 grams per liter of dye. These measurements go out to about 30 minutes, about 33 minutes here. We also did a study where we used the pendular drop technique for measuring interfacial tension, and we measured the same system over about 8 hours. And this curve fit in almost perfectly with the 8-hour curve from the pendular drop. And the extrapolation of this line was pretty accurate in terms of predicting the interfacial chemistry over that time frame. So that's how these were done. We go on. There's also independence in the contact angle. The longer the fluids are in touch with the solid, or the age of those interfaces are, it allows time for adsorption of the surfactant to the solid surface as well, and that can change the contact angle. I'm not going to touch on this too much. One thing I do want to point out is, back here that I forgot to do, is this are all with dyes, with the Sudan 4 dye. The two bottom curves here are a comparison of the Savannah River site M area DNAPL with, in this case, deionized water, and the lower case with a sample of groundwater from that same location. So this is a real mechanism in real systems, not just in our laboratory systems with dyes and essentially pure solvents. Okay. Again, contact angle also shows time dependence. I'm not going to spend much time with that. Okay, here's an example looking at the quote-unquote Sudan family of dyes. When you go into the literature and you look at dyes, there's a vast array of trade names for different dyes. There are three, in the work that I've done in terms of looking at literature research, these three dyes, Sudan 3, Sudan 4, and Oil Red O, are the ones that have been used in the vast majority of research in terms of the visualization of multi-phase fluid flow in porous media in terms of environmentally important compounds such as trichloroethylene, tetrachloroethylene, or PCE, and other things. The only differences are the substitution of methyl groups for hydrogens in these four positions. And again, The work that I'm presenting here was with Sudan 4. All right. I want to look now at what the effects might be. One aspect of the effects of this time dependence of interfacial chemistry on primary drainage can be that there may be an effective interface age or an average interface age as oil drains into porous medium and displaces water. In this situation, I've looked at experimental results from Schwiller's book in 1988, where he set up 3 large diameter columns, basically of 90 centimeters height and 20 centimeters in diameter, and ran them with ran experiments with 3 different sands of varying hydraulic conductivity. 1.2 times 10 to the minus 2 centimeters per second, 8 times 10 to the minus 2, and 32 times 10 to the minus 2 centimeters per second. The mean or median grain diameters, as you see, decrease in this direction, going from here to here. And the distance through which the DNAPL penetrated in these these 2 experiments, experiment 2 and 3, the DNAPL penetrated through the whole column. In the 3rd experiment here, or the 1st experiment, whichever how I set it up, it only penetrated approximately 30 centimeters into the porous medium. Now here's the time down here over which that occurred. In the high permeability porous medium, not surprisingly, the interface is penetrated in about 1,200 seconds. In this lower permeability medium, they penetrated in about 3,600 seconds. In the smallest diameter or smallest median grain size media, where they only penetrated about 30 centimeters, that occurred over this time span of 1 day, or about 86,400 seconds. I'm sorry. I've been saying centimeters for seconds. I didn't mean to. All right. So what can we do with those results? Okay, I'm going to make some assumptions. This is obviously a very idealized set of assumptions, but it can give, just by making these assumptions, we can begin to look at what the possible effects are of that time dependence of the interfacial chemistry on an average interfacial tension that we might want to use to model a process during drainage. We assumed that the porous media were made up of cubic packings of uniform spherical grains of the median grain size. We assume that the flow paths we're tracking are totally vertical, and we assume that each Haynes jump goes through a single pore, and then assume the interfacial chemical kinetics for 1.4 grams per liter Sudan 4 dye. This is corrected for dye content. This is approximately the concentration that Schwiller used in his work. We can look at what the average interfacial age was, and therefore estimate what an average interfacial tension value should be used. This is basically the type of model that I've assumed, where we have cylindrically symmetrical pores and pore throats set up in a cubic array. There's the pores and the pore bodies, or the centers of the pore bodies, basically define a square. Now, if we use these assumptions, we get an average interface age of 43 seconds for the lowest permeability medium, 2.7 seconds for the intermediate permeability medium, and about 1 second for the most permeable medium. If we use the time dependence that I showed you a little bit ago for the dye concentration that I assumed, that leads to an average interfacial tension of 48 for the highest permeable medium, 45 for the middle permeable medium, and only 37 for the lowest permeable medium. That means that the capillary forces, which are controlling that drainage process, are dependent on the interfacial chemistry, dependent on the time or the kinetics of that interfacial chemistry. All right. From there, here I want to show you some preliminary model works or modeling efforts that I did, looking at primary drainage on a pore scale. I assumed a ball and stick type of pore model, similar to what I showed you above. Let's go back a couple and essentially this type of model structure or porous medium structure. We assume the Young-Laplace equation controls interface stability, but now I incorporate interfacial time dependence in, and I also incorporated some variation in pore body and pore throat radii to get some kind of distribution of pore throats within a porous medium. Okay, when we look at the Young-Laplace equation modified for time-dependent interfacial tension, we now have a critical pore throat defined by 2 times the interfacial tension, which is now a function of time, divided by the capillary pressure or the fluid pressure difference between reservoirs on either side of the porous medium. And I assumed interfacial tension kinetics for 0.4 grams per liter Sudan 4 dye in the PCE water system. This is an illustration of the porous medium. Again, it was a very small pore, a total of 49 pores in a 7x7 array, with an apple reservoir on top. In this case, I assumed it was the dyed PCE, and a water reservoir on the bottom. And in analogy to how we measure capillary pressure saturation relationships, I specified pressure heads in the napple and in the water reservoir, and therefore the pressure difference across here, and define that as the capillary pressure for each experiment. This gives you an illustration of the model regions that I assumed. I assumed a coarser grained medium sand to fine sand for an exterior portion of the model, and a fine sand grain distribution for the middle 9 pores in the model. Let's go back here a second. So these middle 9 pores here are smaller in general than the pores on the exterior portion of the model. Okay, here's the model results. If we assume interfacial equilibrium in modeling the result in modeling, if we change the fluid pressure difference, with assuming there's 0 dye concentration, that's what this is up here. This is the distribution, or this is the capillary pressure saturation relationship that we develop. If we assume an equilibrium value of 25.3 millinewtons per meter, that whole distribution is basically shifted downwards. That is, the napple is able to penetrate the medium at a lower capillary pressure. Again, these results have just assumed equilibrium chemistry, equilibrium capillary forces. Right? Now let's look at the results where I assume different capillary pressure differences between the top and the bottom reservoirs, between the napple and the water reservoirs. Those are defined over here in terms of millibars, capillary pressure in terms of millibars. But now I just leave the pressure, that specified pressure, and allow facial chemical kinetics to define what happens in the porous medium. And these are the results. What you see as the time increases, the denapple saturation increases. And what that means is, or what's happening there is, as the age of the interface, a given interface increases, the capillary forces are being decreased through the chemical kinetics of the surfactant, in this case dye, action, absorbing into the porous media. And the fact that these lines are sloped indicates that there is a time dependence to the saturation. And that time dependence, again, arises through the kinetics of the interfacial chemistry. Another interesting aspect to this is you'll note that the maximum saturation that's attained in the experiments is a function of both the dye concentration, in this case the ultimate chemical kinetics, and also the pressure that's applied. In this case, the lowest pressure that's actually applied yields the highest saturation. So the longer time you allow, or actually at lower capillary pressures, the time dependence of the surface chemistry becomes the dominant variable that's controlling the saturation pressure relationship, or the DNAPL saturation.
Dave?
Yeah.
How are these kinetics being modeled? Is diffusion actually being modeled, or is it a prescribed function?
It's a prescribed function. Basically, what I did was take the time dependence data that I showed you previously, and just used a functional fit to that.
Okay.
All right. This graph illustrates the difference. Okay, the difference in maximum saturation that occurred with fluid pressure differences. Okay, if we can go, let's go back a few. Oops, sorry. These results, where we assume interfacial equilibrium, are the primary way that we've modeled capillary pressure saturation relationships to date. That is, as we increase the fluid pressure difference, or the capillary pressure, we get higher saturations of the DNAPL. Oops. Sorry. What I found in this modeling result, which is really surprising to me, is that the maximum saturation that was obtained was actually occurred at the minimum capillary pressure that I applied. This means that the time dependence of the interfacial chemistry has a huge influence on the ultimate saturation results that we get. And this is the form for the particular medium that I modeled. Okay, from the model results, the DNAPL saturation was a function of both time and the capillary pressure applied. The standard view is that saturation is only a function of the capillary pressure that's applied. Also, there were significant differences in the maximum saturation that occurred as a function of the capillary pressure. And what I believe happens is that, if we can go back a slide up here again, this pressure right here, this pressure difference, is the pore entry pressure for that porous medium if we assumed a pure liquid tetrachloroethylene. That is, with no dye concentration and therefore essentially no interfacial chemical kinetics being applied. What I believe happens with these is that as you approach that entry pressure for the pure liquid, there becomes a competition between whether the pressure itself is going to control entry into a porous medium, or the pressure difference, I should say, the capillary pressure, or whether the interfacial chemical kinetics is going to control entry into a given pore, and therefore bypass, say, other pores. All right. Is this real? Now let's go into some experimental results. This illustrates the experimental system that we applied to try and test this work, test this conception. We have a porous medium here. consisting of glass beads, highly uniform glass beads, I might add, in which we set up a column of the dyed PCE over the top of that porous medium. And there was in doing this work, I specifically chose not to use any kind of capillary barrier between the porous medium and the PCE in order to avoid losing some of the dye by adsorption onto that capillary barrier. We controlled the capillary pressure, or the water pressure in the porous medium via a water reservoir burette here. The three-way valve was designed to allow us to get to an equilibrium so we could water height right at the porous medium PCE interface. Just simplified the mathematics. We also, prior to the experiments where we set up DNAPL on top of the medium, we made permeability measurements. So this line was used to allow water to flow through and therefore measure the permeability of the medium via the falling head method. All right. Let me go back a second. Okay. In work that was just published last fall in Water Resources Research, we looked at several experiments where we varied the dye concentration and measured the stable height at which the PCE began to penetrate the porous medium. For the experiments I'm going to show you right now, we ran a very significant series of experiments, or a lot of experiments, and were able to estimate quite accurately what the capillary entry pressure would be as a function of the permeability of the porous medium. And those series of experiments were all run so that the experiment was done within a day. So by doing that, we minimized the influence of the chemical kinetics on those systems. Once we had that, we set up another experiment now where we measured the permeability in the porous medium and then estimated what the entry pressure should be for the given dye solution we were working with. And again, this is the 0.4 gram per liter dye solution that I mentioned previously. The entry pressure for this dye concentration from our previous experiments was about 15 centimeters of height of the PCE above the porous medium. What we did, we set up a column of PCE above the porous medium that was at 12 centimeters. So it's less than the previously measured entry pressure for that porous media. And now we just let that experiment set. Get in closer here. This slide is from about a couple days after the start of the experiment. Just set up for you here. As you can see, let me make sure I synchronize everybody's displays. Does everybody see the close-up?
Yeah, that did it here, Dick.
Okay, great. That small fingers of the dyed DNAPL are beginning to penetrate the porous media. Again, this is approximately a day old. In other experiments, we set up with the lowest dye concentration we experimented with, which was, if I recall right, about 100 times lower concentration, or about 0.004 grams per liter. This interface remained razor sharp over the period of more than a month. So this penetration of these tiny fingers of DNAPL into the porous medium is real. This is a similar illustration. Now you can see, and this is, I think, from about 2 days after the start of the experiment. The fingers have penetrated now about 2 millimeters, the maximum depth of about 2 millimeters. So the saturation is actually beginning to increase in the porous media as we allow the interfacial chemical kinetics to change the capillary force as a function of time. Again, nothing has been changed with the capillary pressure. The height of the PCE column is still 12 centimeters. There's no difference. Then we let the experiment run further. John, do you know what's going on here? This thing is bouncing all over the place.
Let me try here for a second. Can you work with it from there?
Here we go. Maybe we can get it.
And then just synchronize everyone's displays.
All right. My technician, Gary Iverson, who was running this experiment, after approximately 3 or 4 days, nothing seemed to have been changing. Then on the 6th day, now this is 6 days after the start of the experiment, you notice that a little area, let's see, get to my pointer. Oh, jeez. I'm having problems. It's still jumping all over the place. John, do you know what's going on?
I don't. Let me just get it back to there for you. Are you going to need to zoom in definitely, or?
Well, I'd like to. Let's see if we can. Okay, let's look at it. Maybe I can do it with this. I guess you can see it good enough. You can still see it. Okay. All right. 6 days after the start of this experiment, he noticed this little spot of dyed PCE coming to the side wall of the column. Again, nothing has been changed with the system other than allowing the interfacial chemical kinetics, which change the capillary forces, which are resisting penetration of the medium. And now this depth is approximately 1 centimeter into the porous medium. On to the next. Over the next several days, this is now about day 10, the spot darkened, therefore there's more DNAPL, or more of the PCE coming down, and grew. So again, saturation in that porous medium is changing. Again, just as a function of time, just allowing the chemical kinetics to play its role. And then finally, this is approximately a month later. We have the PCE actually has gone through the entire medium and gone out to the bottom. And if you see, you can see that the medium is quite dappled with spots of the PCE appearing throughout the porous medium. Obviously, we can't see what's happening on the inside of the porous medium, but enough has gone through so that the DNAPL actually penetrated the porous medium. Again, the experiment was entirely run maintaining a single capillary pressure and just allowing the chemical kinetics to reduce the capillary forces resisting NAPL penetration of the porous medium. Okay. So what are the conclusions? Surface chemical kinetics are important when we look at and try to understand the multi-phase fluid flow in porous media. That introduces, those surface chemical kinetics introduce time when we try to understand primary drainage. That is, the saturation can become a function of both the applied capillary pressure, which is the standard view that we've worked with so far, and time. The time is important in terms of allowing or understanding the chemical kinetics to play a role in the capillary pressure saturation relationship. The other thing that came out of this work is that the maximum saturation varies with the length of time between pressure increments. That is, when we measure capillary pressure saturation relationships, what's generally done is we increase the capillary pressure that's applied in increments and allow a certain amount of time for the NAPL to flow into the medium and therefore establish a new saturation level at that. depending on the kinetics of the system, if you don't allow enough time, you can get a different capillary pressure saturation relationship. I'm sorry, if you don't allow enough time between increments of pressure, you can obtain a capillary pressure saturation relationship that's different depending on that increment of time. And again, that has to do with the interfacial chemical kinetics. Okay. Let's go. Let's stop right there. If there are people that have questions, let's focus on this part of it. And if we have time, I'll go into the other part of the talk.
Does anybody have questions? It's *1. Talk to the operator, or you can type a chat.
Don Wilson of New Mexico Tech has a question. Please proceed, sir.
Yes, Dave.
Yeah, John.
I want to know what's the propensity for this to occur in natural systems, that is, in systems with no anthropogenic influence, for example, water and air, and the presence of natural organic material in the water as a surfactant.
Yeah, I haven't really given that much thought, John. My guess is it's probably not as important as it is in the pollution realm. In particular, because if you remember, I showed you the comparison with the chemical kinetics, or the interfacial chemical kinetics for the DNAPL at the Savannah River system and the dye systems, that graph. See if I can get back to it real quickly.
The interfacial tension versus time.
Yeah.
You can use that drop-down menu as well, Dave, if you're titled. Right next, just to the right of the slide title, there's a drop-down box there.
I'm not seeing it.
And just to the left of the advance arrow.
Oh, okay.
And you might just want to sync everybody's displays just to make sure that everyone's on the same page with you.
Okay. All right. Again, this is the comparison of the Savannah River site DNAPL in the M area with the dye systems that I worked with. The reason that the SRS DNAPL has a chemical kinetic component to its interfacial chemistry is because it was a used DNAPL. It was used for degreasing purposes during machining operations. When you do that, natural oils, or I should say oils that are used for machining purposes, incorporate surfactants specifically in order to coat the metal surfaces and therefore help cool the process. So by design, surfactants are incorporated into those systems, and when you use a solvent such as PC or TCE to degrease the parts, those surfactants then become, the surfactants and oils become part of the DNAPL. Going back to your question, John, I'm not sure how big an effect this would have on in like an air-water situation. I have not worked with that at all, and I don't have any real sense for the magnitude of change it might introduce. We think about humic acids, however, humic acids and fulvic acids, those sorts of things that would be components of within a root system or a soil system. It's not unrealistic that those could play a role, but I can't tell you anything about the magnitude.
Okay, thank you.
Yep.
Dave, there's a question from Rod Bowman at New Mexico Tech in the chat box.
No, the modeling that I did not incorporate anything with the time dependence of the contact angle. That could also play a role. I think that's also particularly when we get to slower or lower applied capillary pressures, where the kinetics of the interfacial chemistry play a role. In that situation, the contact angle time dependence probably should be incorporated. There's some things that I've seen that suggest, or some work that I've seen that suggests that the contact angle doesn't play that big a role in terms of controlling the processes in porous media. I'm not convinced of that, but for this purpose, for this modeling purpose, I did not incorporate the time dependence of the contact angle.
Ron Bowman here. What I was really trying to get at there, and I think you addressed it, was how big the effects of the changes of wettability.
Let me see if I can go. Because you basically, here's the I'm going to make sure I think everybody's displays. Here again is the contact angle information as a function of interface age. You see relatively large changes in contact angle over the time scale of about a half an hour. However, when you take the cosine of that, which is how it actually comes into play in terms of the capillary balance of Young's equation, the change is probably not that significant.
Rachel, are there any other questions?
Yes, Zhao Tag of New Mexico Tech has a question. Please proceed, sir.
I think that was a mistake. Go ahead to the next question.
Sorry, what?
Charlie Worth of the University of Illinois.
Yeah. I was wondering, on your column experiment, how do you separate out the effects of the permeability, I guess, affecting the time that it takes for that front to move down, or for the DNAP to follow some preferential flow path? Is that experiment alone conclusive that you have this change? Is that how you interpret the experiment based on your, say, plot or slide 31 of 61 here, where you show the contact angle versus interfacial age, and also the, I think it's the previous slide where you had the interfacial tension versus the time?
What we did was, and this work was published last fall in Water Resources Research, we ran a series of experiments, a long series of experiments, where we used just undyed PCE. Therefore, there's a minimal chemical, if you remember the, let's see, let me go back a slide here. We ran a whole series of experiments with the single porous medium, same glass bead grain sizes, each experiment, and then measuring the entry pressure. Using that series of experiments, there's essentially no influence, and using the undyed PCE, there's essentially zero influence of chemical kinetics on the penetration rate. When we started incorporating dyes, we ran experiments up to a dye concentration of 1.37 grams per liter. The entry pressure that we measured for those media decreased as the dye concentration increased. That is, as the capillary forces were diminished due to the surface active nature of the dye. All of that series of experiments with the undyed porous media were all run in a matter of a couple hours, and it becomes a very complex issue to kind of untangle the chemical kinetics of the dye and the penetration time for the porous media, the given porous media. But you could see. Does that answer your question?
Yeah, I'll have to think about it a little bit, but thanks.
Yep.
There are no further questions on the audio bridge at this time.
John Wilson has typed in a question here. Okay, actually there's another question. Let's see. Okay, from Dartmouth, a related question. Do you think the permeability was different where the grains were in contact with the glass in your column experiment? That's a good question. My gut sense is no, and this is the reason. When we set up those experiments, we set up the glass beads, treated the glass beads, and then we ran water flowing downward through the porous medium for a significant amount of time in order to try and compact the porous medium as much as possible. And actually, we were able to measure permeability changes as a function of that time. We could measure the permeability before running that compaction, or actually, sorry, we would measure the porosity of the porous medium before running the water through and then after the running water through, and you can see that there would be some changes. There actually may be an influence of the dye itself as it wedges its way into the porous medium. It may loosen that upper level of porous media somewhat, but without any kind of specific measurements such as X-ray measurements or something like that, where we could actually detect the any changes. I can't say that that's not a factor. Okay. And John Wilson, consider the column experiments with different capillary pressures. Does the higher oil saturation for the lower capillary pressure indicate that aging leads to lower bypassing? Yeah, I think that's the case. When I ran those model results that I showed you, I actually ran them by hand in order so I could see really what was going on. And what you observed is that at the lower capillary pressures, the time dependence of the capillary forces, the time dependence of the interfacial chemistry, becomes the dominant factor that controls where and when interfaces when pores are penetrated. And I think that is the issue. That is what happens, that bypassing of pores diminishes when the chemical kinetics are incorporated over a long time span.
Rachel, are there any other questions in the queue?
Not at this time, gentlemen.
Okay.
Does anybody want to see the rest of the...
Dave, just so you know, we've already lost a couple folks, and a couple more have chatted in that they are going to have to run shortly.
Okay.
So for those of you still online, though, the presentation posted on the Kawazi website does have the remaining slides. So if you'd like to take a look at that, you could certainly send me an email, and I can pass that on to Dave. But Dave, thanks a lot for your talk. It was very interesting.
My pleasure. Thanks, John.
Ladies and gentlemen, thank you for your participation. This concludes today's conference. You may now disconnect.